Brain training has been shown to improve attention and reasoning in studies which test a person's ability to retain and manipulate information. Games such as concentration or memory have been used to assess the effects of age on memory. A large variety of games are available to improve one's own memory. This project produces a memory game. The game itself consists of the PMOD CLS display, the LED matrix, and the PMOD keypad components from Diligent's Embedded Systems Kit, as well as NI MyRio. This game uses LEDs to indicate a corresponding keypad character sequence to enter. The LED matrix is divided into a 4x4 grid, each cell containing 4 LEDs. Each group of LEDs corresponds with a key on the keypad. The game randomly selects a series of character positions and lights them in the order they were chosen. The player then presses the character keys in the sequence shown. Each successfully entered sequence advances the level of play. The number of characters randomly selected and the amount of time each group of LEDs is lit is determined by the level number. The player is first asked, "Begin game?" Selecting 2 for no ends the game. Selecting 1 for yes starts level 1. Watch the yellow lights carefully as they are displayed in order to repeat the pattern. Pressing the wrong key lights the selection in red and gives the player the option to return to level 1 or quit. Pressing the correct key lights the selection in green, and correctly completing the sequence gives the player the option to proceed to the next level or quit. Level 1 consists of 2 characters and displays the appropriate group of LEDs for about 2.5 seconds with a half-second pause in between. Each subsequent level adds 1 character and reduces the display and pause times by 10%. The PMOD CLS display provides options, instructions, and results to the player, and the game is continued until the player elects to quit. Here's how it works. This game was programmed using a Windows 10 desktop PC running LabVIEW 2019 with real-time software. The hardware components are National Instruments MyRio, Diligent's PMOD keypad and PMOD CLS, and Youngson's YSM2088CR3G2C double color dot matrix, hereafter called the LED matrix. The components are connected together using 12 female-female jumper wires, 24 male-female jumper wires, and 2 400-point solderless breadboards. The block diagram shows how the components are combined and the direction of data flow. The National Instruments MyRio 1900 is a portable, reconfigurable input-output device for use by students to design control, robotics, and mechatronic systems. The MyRio provides the electronic brain for the game. MyRio's expansion ports A and B carry identical sets of signals allowing communication with peripheral components. For this game, all 32 digital input-output connections, both 3.3 volt power connections, 1 ground, and 1 UART-TX connection are used. Diligent's PMOD keypad consists of 16 momentary push buttons electrically arranged in isolated rows and columns, allowing accurate detection of 2 simultaneous button presses. This device communicates using a 12-pin port with general-purpose input-output interface. The 12-pin port is header J1. Each column and row has its own dedicated pin, and only 1 power supply is required for operation. These are the electrical connections used between MyRio and PMOD keypad in this project. Among the first tasks completed in the program is opening the channels to PMOD keypad's column connections. This ensures that PMOD keypad can be accurately read throughout the game. When input from the player is called for, each column channel is individually accessed, given a value of Boolean false, and applied to the connections for each row. Any pressed key generates a false for that row associated with that column. This data is used to build a 1x4 array, which is then reverse ordered and inverted before being concatenated into a 4x4 array as output from the VI. The values in this output array will be all false except for any element associated with the pressed key. Diligent's PMOD CLS is a 16x2 liquid crystal character display with a wide range of instruction functions. Capable of multiple communication options, the Universal Asynchronous Receiver Transmitter Protocol is used in this project. This device provides communication options using 2 1x6 pin ports. The desired communication protocol is selected by jumper positions. The UART protocol at 9600 baud is used. Header J2 provides the required connections, which are the power supply, ground, and receive data pins. These are the electrical connections used between MyRio and PMOD CLS in this project. Along with the initialization of channels associated with PMOD keypad's columns, MyRio's UART output to PMOD CLS is formatted. The commands given wrap text at 16 characters, clear the display and home the cursor, and turn the cursor off. Throughout the game, all messages sent to the PMOD CLS will wrap to the second line on the 17th character and the cursor will not be visible. Only the instruction to clear the screen and home the cursor will be repeated for every message sent to the display. PMOD CLS interface VI is identical to the initialization VI with the exception that the input to UART varies. This VI does not include the instruction to clear the display and home the cursor as it is included in higher level VIs. The Young Sun LED Technology Company Limited LED Matrix is an 8x8 dot matrix LED display. This LED matrix is capable of producing 3 colors: red, green, and through a combination of both, yellow. The LED display contains 128 individual LEDs. Each of the 64 positions on the 8x8 matrix contains 2 LEDs, one red, one green. Even though yellow is produced by use of both, they cannot be energized together. Each diode is connected to 2 of the 24 pins, and carefully controlling voltage input allows great versatility in display. These are the electrical connections used by my Rio and the LED matrix in this project. Combined with those of the PMOD keypad, all 32 digital input-output connections available on NI myRio's MXP ports are assigned. LED matrix interface VI cycles through the red and green LEDs for each row in rapid succession, one state per iteration of the for loop. A time delay slows the performance of the VI and provides a starting indication time of about 2.5 seconds. A second for loop provides a short pause between position displays. The total number of states in LED matrix interface VI is 41. 5 states for each of the 8 rows plus the start state. Start is always the first state and places all LEDs in the off condition by applying a true to the rows and a false to the columns. Enable row 1 connects an external input to row 1. Enable green 1 connects that external input to the green column. Because only one color for one row is enabled, only the green LEDs in row 1 can be on. Clear green 1 applies a false to the green column and prevents green LEDs from being on. Enable red 1 and clear red 1 perform the same functions for the red LEDs in row 1. Enable row 2 completes the operation of row 1 by simultaneously connecting a true to row 1 and the external input to row 2 prior to continuing on. The final state in the list, clear red 8, sends the VI back to enable row 1 to continue the LED sequence for the number of iterations applied to the loop. Due to the construction and dimensions of the LED matrix, it is mounted on a combination of 2 400-point breadboards to provide a stable base with access to all 24 pins. The path followed by the game for every situation is shown in this flowchart. Now we'll take a look at the code that makes it work. If you recall, the output of the PMOD keypad interface VI is a 4x4 array of Boolean values. The PMOD keypad input VI indexes that output into its component 1x4 column arrays. Each of these arrays are searched for a true. When one is found, the while loop is stopped and the output arrays are built. The array containing the true is passed directly to the output column array, and the results of the column search are passed to the output row array. Each element of both outputs is doubled, creating 2 1x8 arrays. The row output is then inverted. This produces arrays that can be directly applied to the LED matrix interface VI with values representing the key that was pressed. The question VI takes the column and row arrays from the PMOD keypad input VI to determine the player's response to the question asked. Only 2 possible responses are accepted, and any result other than 1 or 2 results in a message, please select 1 for yes or 2 for no. For the row array, only a false in element 0 is accepted. From the column array, a true is accepted from either element 0 or 2. These results correspond to a key press of 1 or 2. When an accepted key press is detected, the loop is stopped and the appropriate response is displayed according to the question input cluster. Otherwise, the loop repeats. Note the clear display and home cursor command is issued along with the response. Similar to the question VI, prompt VI presents options to the player. The difference, however, is that prompt VI looks only for a key press as the follow-on VI is question VI. As there is no time delay between functions, any key pressed will remain pressed until after question VI evaluates the input and responds. In this way, question VI appears to be bypassed. The welcome VI provides input to question VI asking the player, begin game, 1 for yes or 2 for no. If 2 is pressed, the message "Until next time, have a nice day" is displayed and a true is sent to end the game. If 1 is selected, the message "Great, here we go" is displayed, welcome VI is complete, and select and display starts. Message VI is another application of the PMOD CLS interface VI, which simply displays a message. The Select and Display VI displays a message to watch the lights carefully as positions are shown on the LED matrix. These positions are chosen by 2 random functions generating values between 0 and 3. Each result is passed to a case structure which provides the appropriate output array associated with the row or column. The arrays are bundled into a cluster. The top position in the cluster is the row, followed by the green column and the red column. Note the lower case structure provides its output to both the middle and lower positions of the bundle cluster function. This presents the positions in yellow. The output of both case structures is also used to build an array to compare with player input. The Enter Sequence VI takes the player's input, compares it to the output array of Select and Display VI, lights the player's selection in red if incorrect and green if correct. If the incorrect key is pressed, the player is informed level failed and is given the option to continue. If the correct response is entered, the subsequent player selections are compared in sequence until the sequence has been successfully repeated. The player is informed level completed and given the option to continue, while sequence length is increased and cycle time is decreased. Tying it all together is the top-level VI. Project Main VI consists of a flat sequence structure. The first frame creates an error cluster and forces PMOD CLS and PMOD keypad initialization VIs to be performed before any other action can take place. The second frame contains the majority of the code and uses while loops to control the flow of the game. The final frame contains instructions for when an error is encountered. The output of the error cluster is threaded through many of the VIs used in this project to control the resolution of any error encountered. Testing for this project was performed at every level. Individual components were tested to ensure proper operation. Testing the LED matrix quickly identified a wiring error which produced erroneous indications. The performance test verified all intended features worked correctly and any problems were corrected. One such correction inserted a time delay to the LED matrix interface VI, providing a break between light positions. The stress test replaced user input with the game's own selections in order to determine if there was an upper limit to the number of levels. While no upper limit to the game's capability was detected, the sequences quickly became difficult to follow. With the testing complete, the code restored, and a successful final performance test, the game program was compiled and deployed to MyRio. The game now runs independently of the computer. In closing, memory games may be helpful in training the brain to quickly and efficiently memorize sequences of data such as phone numbers, names in a group, or other pieces of information that cannot be connected by reason alone. The game presented in this project is one such game. This concludes the presentation. Until next time, have a nice day.